So I want to present Thomas Schlumprecht from Texas A&A. But since we are, as it seems, mainly people who are related to Banach spaces, that is why I'm just letting Thomas speak for himself. His slides will do that.
Okay.
And thank you Thomas, for agreeing to speak.
Okay, thank you very much. Thank you very much, Denka. So I'm speaking about joint work with Florent, Pavlos, and Andras, Lamplighter metric spaces and their embeddings into L1. It's kind of a new subject for me, so I'm a little bit nervous. There are probably more specialists who know better than I do. And let me first kind of give a couple of reasons. Why do we want to embed metric spaces into Banach spaces? There are a couple of reasons. One of them is, for example, the Ribe program generated by Bourgain, who characterized the not super reflexivity of a Banach space by embedding uniformly or by Lipschitz binary trees in connection to the Coase-Baum conjecture or Coase-Novikov conjecture is also interesting. You, for example, proved that finitely generated groups which Kurzweil embeds into a Hilbert space satisfy the Coase-Baum conjecture, and Kasper and you proved the same for the uniformly convex Banach spaces in terms of the Coase-Novikov conjecture. Another reason is Linear, London, and Robinovich showed that by embedding graphs into L1, you can get efficient algorithms for certain problems, optimization problems, like, for example, the sparsest cut problems. But the most important reason, in my opinion, is it's hard, interesting, and fun to do these problems. And it involves a lot of mathematics. I mean, it's not only Banach space theory and graph theory, which you would expect, but it's sort of probability theory. There's also harmonic analysis, Fourier analysis on abelian groups is involved. So a lot of mathematics comes together there. So let me explain what the Lamplighter metric space is before I say what the Lamplighter graph is, because it's kind of more general. So we are starting with I have this finger here. You see, we are starting with a metric space and look at a finite subset in 2 points. And now, well, the traveling salesman problem asks for the shortest walk from X to Y, visiting all points of F. So if you want to have it formally, TSP XFY is the sum of all, you order the union of X, Y, and F into a sequence, starting with X and ending with Y, and add up the distances, and you look at the infimum of that. The reordering which gives you the infimum. Now, the Lamplighter metric is then simply the traveling salesman problem from X to Y going through the symmetric difference of A and B plus the cardinality of A and B. If you only have the first part, then this would be not a metric, because I think if you do, for example, if you write X and the singleton X and the empty set, these have a traveling salesman distance of 0. So you need also the second part. And it is then more connected to the Lamplighter graph, which I want to explain now. So you start with a graph, and I'm considering a weighted graph. So it's a triple. You have the vertices, which are the points, then the edges, which are a subset of all subsets of 2 elements, and you give every edge a weight, which is then the distance, a positive weight. Then a walk in the graph is simply a sequence, x, b0, b1 until bn, for which every consecutive elements are an edge. And then you can define the length of a walk simply by adding up the weights. We call this the length of the walk. And then, well, a path is then a non-repeating walk. And then we always assume all our graphs will be connected so that there's at least one path between every x and every y. And the path with infinite lengths will be our distance from x to y, our metric. So this will be then the graph metric. This will be called the graph metric, okay? Now, giving such a graph, we can now define the Lamplighter graph on top of it. This will be a graph which has, okay, it has the vertices are all the pairs x, a, where x is an element in, x is a vertex, and a is a finite subset of the vertices of my ground graph. There will be two kinds of edges. The first kind comes simply, an edge is x, a and y, a, so the second coordinate is the same, so that x, y is an edge of our starting graph, and we call this a walk. The other kind of edge is x, a and x, b, so these are the same. And we require the symmetric difference of a and b to be exactly the singleton x. So what is the interpretation? And then the weight for the first kind of edges, the weight is the weight of xy, of our edge in E. And the second weight is simply 1. So for the switches, we have simply the weight 1. Okay, now what is the interpretation is now kind of clear. If x is the position of the lamplighter, A are the position of the lights which are switched on, Y is the position where the lamplighter wants to end up, and B are the positions of the lamps which should be switched on in the end state, then the lamplighter distance is then the transportation, traveling salesman distance from X, symmetric difference B and Y, and the cardinality of AB. So these are the number of switches, and this is the shortest walk from X to Y going through the symmetric difference of AB. Any question? Any questions? Okay. So now, what do I mean by Lipschitz embeddings? Let me also recall that we have two metric spaces. We have I can assume an injective map from X to Y. Then we call the distortion. I first take the quotients between the distance of f of x and f of y divided by the distance of x and y, and take the supremum over all x not equal to y, and then I put the opposite. This is then clearly the Lipschitz norm of f, and here I take the distance in x or of x and y divided by the distance of their images, and this is then of course the Lipschitz norm of the inverse defined on the image. Okay. Now, the y distortion of x, which I denote by cyx, it's the infimum of all distortions of f, where f goes from x to y. And then I'm looking at a class of metric spaces, and I call the m distortion of x the infimum of all the m distortion of x where x is in the class. So in other words, it's a double infimum, the infimum over all m the class M, and the infimum of all maps from X in this metric space and its distortion. And we are interested in two classes here. We are on the one class will be the trees with weights. So these are, I will be a little bit more careful next in a couple of minutes, but for the moment, the trees are simply graphs which do not have cycles. So in other words, what it really means that if you have an X and an Y, there's exactly one path from X to Y. There's no other shortcut or something like this. You have exactly unique path between two elements of your tree. And the other class is, because we want to embed it into, we want to embed graphs, is the L1 spaces. For me, L1 spaces, they will practically, almost all our graphs will be finite. So these are really, you can as well say, all the L1 ends, right, as a class, but okay. So let me now present the results we have. The first theorem is that a weighted tree can always be embedded into L1, the lamplighter of a tree can always be embedded in one with distortion equal or less than 5. Then using stochastic embeddings, and this will be a very important term in my talk, using I will define it later, using stochastic embeddings of metric spaces, we can then deduce that every metric space which has n elements can be embedded, or the Lamplighter graph, the Lamplighter metric space of that can be embedded in L1 with up to log the number of elements. So the distortion is, and using that, it's kind of optimal. Using stochastic embeddings, I mean, we don't know whether we can do better in specific cases, but if you insist on using stochastic embeddings, you cannot do better. And the last theorem I want to discuss, we want now to embed the Lamplighter group, which is actually a group, but also Lamplighter graph on the infinite lattice of dimension d. Think d of equal 2. This is the into L1. We do not know whether we can do this Lipschitzly, by Lipschitzly. We do not know this, but we can find a map which has a Lipschitz upper bound. And it has a lower bound, well, which is up to a log times log bound Lipschitz. But so it's not quite Lipschitz, but it's the distance of the image is bigger than the distance of the pre-image times, well, like of this one, divided by the log times log of the distance. Okay, any questions? Okay, so let's discuss what a stochastic embedding is. So this is was I think in our knowledge formalized the first time by Bartel 1996, but of course the idea is of use was used before everything. I mean, in some sense, it's often so that choosing something random gives you better bounds, and this is the idea which is behind that. So we are given a class of metric spaces, and we are giving a fixed metric space, x dx. Then we have a finite family of functions. You can also define this in infinite case, but for simplicity, I will do it only for finitely many. We have a family of functions which maps x into some representant of our class. Let's call them mi with a metric di. And we have a sequence of positive numbers, 1 to n, which adds up to 1. So I think this of being a probability. Then we say that this family of functions together with this probability is called a d-stochastic embedding of x into m. If for all x and y, we have a lower upper bound, so it's the inverse must be Lipschitz 1, so a deterministic lower bound, but the upper bound is only in expectation. So if you take the expected value of the di of fix, of the distance in di of fix and fiy, which is simply the sum, this convex combination, you get a constant d, this is why it's d stochastic, times the distance in the original, in x. Okay, so in other words, in average, it's d Lipschitz. This is more or less the idea. In average, it's d Lipschitz. And we say the stochastic M distortion is then simply the infimum of all d for which there is a stochastic embedding of x into m. Okay, let me discuss the properties or the good properties of these stochastic embeddings. First, they can be much lower, the stochastic embeddings can be much lower than the distortions, the distortion. Here, let me give you an example. I think this is like an extreme example. You take a circle. Now you want to embed this circle into a tree. Right? And I think intuitively it's clear, if you want to do this, you have to cut one edge. And by cutting this edge, you make out of these two neighbor points, points which are very far apart. This is intuitively clear. But if, and it's really, if you want to bijectively map a circle into a tree, the best you can do is simply putting it into a line. But then, of course, 0 and n-1 get very apart, right? But then, if you only require this to be an injective embedding, there's a proof by Rabinovich-Ras, which used algebraic topology, and then there's an elementary proof by Gupta in 2001, which says the distortion of a circle into trees is always bigger or equal than n-1. So it's n, more or less. It's a multiple of n. Nevertheless, it is clear that the stochastic embedding of a circle of length n is always smaller than 2, because what you can do is you can do this cutting, this map. Okay, so let me you do this map for every x. So you do this for every x, and then you average. So the distortion at this point will be of the order n, but then you do it n times and you take the average, so you get n times n divided by n is 1, so you get a distortion of 2. So you make here the stochastic distortion of a circle into a line is 2, while its distortion is linearly n. Okay, this was one reason. And actually, there's a much better result, or much more general result, by I never can pronounce his name, Charon-Paul, Rao and Talva, 2004. They proved the following, that if you have a metric space with n elements, so any metric space with n elements can be stochastically embedded into trees up to a factor log n times some constant. I think it's 48. So this is a very important, this is a result we will use. And another property of stochastic embeddings is the following. If a metric space destochastically embeds into a class M, then the same happens for the corresponding Lamplighter metric spaces. So then the Lamplighter of X destochastically embeds into the Lamplighter M of the class. This is a very general, actually, this proposition can be generalized. It's true for many other derived spaces, like, for example, also for the Wasserstein spaces. So you can get embedding as that. So, and finally, the last good property of stochastic embeddings, it is very compatible with L1 spaces. What do I mean by this? So assume you have a metric space X dx, which admits a destochastic embedding into a class of metric spaces M, and you know that the L1 distortion of X is up to the same factor D, the L1 distortion of the class M. So if you can embed the class M very well into L1, the same happens for X. And the reason is very simple. The reason is simply because L1 is the L1 sum of L1. So if you have mappings from X to MIs, and then you have these probabilities which add up to 1, and you have mapping from MI to L1, you simply look at X going to this vector of G of F1, G2, F2 with these factors, and then which you think in this L1 sum, which is of course the same as L1 again. So this is a very simple argument. It fits very well with L1 spaces. Okay, so now let's embed the Lamplighter space of trees into L1. How to do this? So from now on, I will fix a tree, a weighted tree, and for X and Y in V, I call the interval XY is the unique path in T from X to Y. Then for any subset of V, I define X comma A, simply the union of this path. So this is, so you have here X, and then you have here some A's. So it's like that, it could be like, so for example, and then another A, right? Okay, so it's simply a subtree where, of course, there could be an A here, but all the leaves of this tree will be in A. Okay, now there is a closed, it's not very hard, at least not, it's not intuitively, it's not very hard to see the following closed formula of the traveling salesman distance. The traveling salesman distance X through A to Y is 2 times the edges on the subtree minus the edges, minus the edges which go directly from X, Y, plus the edges from X to Y, you count 1. So the edges which are not in X, Y, but are in this set, you count them twice, and the other, the edges from X to Y, you count only once. And this is quite simple. Well, at least, I mean, it's maybe a pain if you write it down, but so let's say this is the image. And then there are some sets in A. So now you, for each element in your A, you have a unique way to X, and this might or might not hit on this way. So it could be like this, or it could be like that, or it could be like that. So now, what is the traveling salesman has to do? He does the following. He starts at X, then this will be the first position he visits. Then he goes along, well, let me say here. Then he goes to this point, then he visits this, but has to go back. And here he also has to go back. So whenever he has to leave the main road from X to Y, he has to go back and forward. So he always has to go back and forwards. So this is where the factor 2 comes in. And on the direct path from X to Y, he only has to take each edge only once. So this is to explain the traveling salesman distance. And now we want, so for the embedding, we will argue the following way. Let us remember that a metric space MD isometrically embeds into L1 if D is a positive linear combination of cuts. So in other words, it's a cut matrix. So what I mean by this, that dx and y can be written as positive numbers times cuts. And a cut is simply, you take a set S. If x and y are in the same, either both in S or both in the complement of S, it's 0. And if the one is in S and the other is in the complement, it's 1. So this is a sum of cut metrics. And so we want to define, so our goal is to define a cut metric on the Lamplighter graph of a tree, which is up to the factor 4, equivalent to the Lamplighter metric. Okay, so for fixed Z and for fixed E and for a finite number V, we let S Z is C be the set of all elements in C for which E is the edge E lies on the direct way from Z to C. So in other words, you have Z, and then you have some edge, and then you have points. And a point of C is in that set if in order to go from Z to that point, you have to go through E. So this point will be in S. Z, E, C. If you don't go, for example, if you don't have to go through E, then it's not. So this is the definition of this set. And now what I'm claiming is, if X and Y are vertices and A and B are subsets, sorry, something, okay, sorry. Okay, if E is a edge from X to the symmetric difference, then these two sets are different, so they can be cut. Why is this true? Well, let's do the picture again. So let's say X here. It really doesn't matter. The Y doesn't matter so much. So, and then you have this edge here. And so here is something. So if E, first of all, assuming you have an E, these two elements cannot be the same. A cannot be equal to B. So there must be some A in A, so without loss of generality, some A in C. So if this A is here, but not, sorry, if this A is here, but not in B, this A must be here. So, but it cannot be there because it's not on B. If it's not in the set, if A is something like that, then I have, now I'm getting, I'm forgetting the argument. If A is not in, so if A is not in, if A is in A but not in S, X, E, A. Then Florent, why is it true? Okay, I'm sorry, I forgot this argument, but it's also a very simple argument. And then you define your cuts, you define as being for every E in E, for every subset of V, but every subset which is not empty, you define CEZ, the set of all vertices in the Lamplighter vertex, in the vertices of the Lamplighter graph, for which Z equals to this set. And then you add up, you're taking the cut with these sets. Sometimes it doesn't work. Okay. You're taking the cut with respect to these sets. Your lambda will be the weight of E, and then you sum up over all subsets which are not empty, and then over all E. Now, the important observation is that if you look at this set, fix your E and look at this set, it can only be 0, 1, or 2. It is 0 if the two sets are equal. If for X and Y these two sets are equal, then it must be 0 because they will be in the same thing. It's 1 if it's 1 if one of them is not empty, the other is empty, or vice versa. Yeah, and it's 2 if they are not equal and both not equal to 0. And this implies easily that the total sum is finite, because even if the tree is infinite, it's finite. And then from that observation I just talked, you can show, this takes a little while, you have to consider different cases, but it's quite very elementary. You have to simply count, but it's quite, it takes a while considering all the cases. Then you can have a lower and upper estimate. You can define that this is smaller than 2 times this, and this is, of course, remember, 2 times this plus this, so this is actually 2 times the traveling salesman problem from X, A, B, Y, and this is bigger than this. Here, what is still missing for the traveling salesman distance, it's the sum over all E's in X, Y. But now you add to both this term, then you have on the left side the Lamplighter distance of XA to YB divided by 2. And you have on the right side, after estimating, the 2.5 times the Lamplighter distance from XA to YB. And this is, so you have a distortion of 5. Okay, so this is the embedding of Lamplighter trees into L1 up to the distortion 5. And now, using the lifting property I just told you before, and now the theorem of Fakcharanpur, Rao, and Talwar about the stochastic embeddings, you then quickly get the corollary that every metric space with n elements has a L1 distortion, here it should be L1, of 5 times 48. The 5 comes from the tree and the 48 from the theorem. This is the best possible because this is the best possible if you want to use stochastic embedding into trees, because if you have an unweighted graph and a stochastic embedding into, you can also compute the average distortion. we have a mapping from X to n, and you compute the average distortion. And then using the fact that circles behave very badly to being into trees, you can then use the result of Rabinov-Raz or Gupta, that if you take the torus, the discrete torus, like, and the discrete torus has a lot of circles, and every circle, when you embed it into a tree, must have a bad point. So if you count the number of circles, and I'm only using square circles, and you take into account that the same point can be a bad point for different circles, and then you add up, you get an average distortion of log n. So you have that the discrete torus of dimension n has an average distortion of a constant times log n. So in other words, you don't get anything better. So here should be average just into trees. Okay. Now let me go to so I have 10 minutes, so I think I can discuss the last result, how to embed the Lamplighter of the infinite grid. And let's simply think of D being 2, the infinite grid into L1. So the infinite grid, right? It's this, sorry. Forever, right? And so, and we want to use the finite result. And what do? We need some mapping from the infinite grid into the finite grid. Of course, the first map which comes into mind, it's simply taking everything modulo n, right? Mapping Z into Z modulo n by taking the quotient back. This is not good because it gives you a bad distortion. But I'm doing what I'm calling a folding map, and I will give the picture in a minute. So I'm folding, I'm mapping, I want to map ZD into the finite n by n grid, ND, by doing the following: Z1, Z2, ZD goes into some phi of Z1, phi of Z2, phi of D. How do I define phi of D? Phi of I times every number can be, of course, written by multiple of n plus j, where j is smaller or equal n minus 1. So if I is even, I use the modulo map. But if I is odd, I should have said this here, then I'm using kind of the inverse of I'm using n minus j. And what am I doing? Let me make this picture clear. Let me make this here. What I'm doing is the following. I have here my n, 1, 2, n minus 1. And so I'm writing Z as a kind of an infinite serpent. This is my Z. And now I'm simply projecting down. This is what I'm doing. So in other words, n goes into n minus 1, n plus 1 goes into n minus 2, n plus 2 goes into n minus 2. So I'm kind of zigzagging and projecting down. Now the problem is that I don't like that this is not injective. I want to make neighbors apart from each other. I don't care if something far away is not injective, but this is a problem I don't like. So what I do, therefore, I am looking at a shifted version of my folding map. And this looks then like that. Sorry. So what I'm doing, I'm looking at shifted version by simply starting with a V. So this is 0, this is V, and then going this way. So at least for all, but for many V's, I have injectivity. And then I will average over the V's. So this will be, so I'm going now this. Well, actually, this is minus V. Okay. Okay, so I having now these shifted folding maps. And now, okay, now I'm simply extending these folding maps to a map from the Lamplighter on the grid to the Lamplighter on the finite grid, simply by saying x of A is simply the image under V and the image of A under V. This gives me, this is not injective, but, and then I think the best, after experimenting a little bit, the best is to take n to be 2 to the 2 to the L. I'm now fixing L, n, and n is equal to 2 to the 2 to the L. And then I'm considering an embedding from the Lamplighter of the finite grid of length n into L1, which I had by my previous result, which is Lipschitz, but has this lower C over log n estimate, which I can do by what we did before. Then, okay, so this is I'm fixing for every L and for every N such a map. For every L, I'm fixing such a map. I'm considering the unit. Now I have to take the average over all shifts. I take V to be the uniform measure on ND, and I'm fixing a sequence of ALs which add up to 1. Then I'm mapping the Lamplighter of the infinite grid into L1 of the vector valued function, new 1 into L1, which is of course again the same as little 1, but I want to think of it this way, simply by saying G of Lx goes into, I'm applying first my folding map into this, and then I'm applying this GL. And then I go from the Lamplighter, I'm simply adding up all these maps, but I have to, of course, be careful. I have to adding up with this coefficients of numbers which add up to 1, to keep the Lipschitz 1 condition. And this is yeah. Let me go quickly. So if you look, where is this? Oh. Yeah, so if you look at the proof, then this log t comes from this log t, and the log t comes because I had to add up the AL and make them smaller and smaller. This will be this. This is, yeah, this comes from that, and now this comes from the ALs, and so we proved that result. What is not known, so I told you that using stochastic embedding, you cannot do better than that. But it's not known whether you cannot, what is the lower estimate. So it's actually still possible, theoretically, I don't believe it's true, but it's still possible that the Lamplighter on metrics, no, this is not possible. But like, for example, the Lamplighter of the grid, it's not known whether this cannot uniformly embed into L1. It's not even known whether the infinite grid could not embed by Lipschitzian L1. And I think I think I'm ending a little bit early, but I think this is not a problem. Okay, so thank you very much. I'm done.
Thank you, Thomas.
Yeah, I think I went too quick, but I wanted to go back. I wanted to make sure that I get the folding map, so because I think I like that. Okay.
Well, any questions? I mean, I wanted to ask here, when you have these stochastic embeddings, in your case, you used like discrete case into finitely many. I mean, well, not finitely many, but you have like P1, P2, and so on. I suppose for this type of questions, there is no point of having it like continuous.
Yeah, I mean, you can define it for continuous. You have to there's probably some measurability assumption you need, but yes, you can actually define stochastic embeddings.
Yeah, but for this type of problems, probably
for this type of problems,
won't give you anything.
Yeah, I don't see any good application for that.
Right, right.
So it works also for the Wasserstein, but
yeah,
and there you might have infinite, right? But I think so. Well, I'm not sure.
I don't know, somehow for finite graphs.
Well, you could at least have, okay, so I think that, I mean, if you look at least discrete, a sequence. That
right.
Be, yeah,
for sequence, yes, but for
sequences, infinite sequences might be, but for like continuous, like Lebesgue measure, for example, for uniform measure, I don't have any application.
Somehow doesn't feel fit for this type of problems.
Yeah.
I don't know, but doesn't feel so. Any questions? Well, if not, let's thank Thomas once again. Thank you.